So, how secure are the AI models we're all using every single day? We're about to look at a pretty startling new vulnerability that suggests bigger isn't always better when it comes to AI safety. In fact, it might just be the total opposite.
All right, let's get straight into it. For the longest time, the thinking in the security world was that to mess with a huge AI model, you'd need to poison a really big chunk of its training data. Which, hey, makes sense, right? The bigger the haystack, the more needles you'd need to hide. But this new research just throws that whole idea out the window. The new reality? It doesn't matter how gigantic the model gets. The number of bad documents you need to poison it stays shockingly, and I mean shockingly, small and constant.
And that's the big question, isn't it? When we say a small number, just how small are we talking? What's the magic number that can crack a model trained on an ocean of data? 250. That's it. I mean, that number is so small, it's almost hard to wrap your head around. With just 250 poisoned documents, researchers could sneak a hidden vulnerability, a backdoor, into models with billions and billions of parameters. So let's break down how this actually works. This isn't some kind of brute force attack. It's way more subtle, way more insidious. We're talking about something called a backdoor attack. And this is what makes these attacks so sneaky. A model with a backdoor will act completely normal, like 99.9% of the time. You can ask it questions, you can have it write code, do whatever, but the moment an attacker uses a very specific, secret trigger phrase, bam, the hidden malicious behavior kicks in. It's basically a sleeper agent, just waiting inside the AI. So to really test this out, the researchers went right for the foundation. They targeted the most fundamental stage of an AI's life. It's pre-training. This is where the model just soaks up massive amounts of text from the internet to learn the basics of language, way before it's fine-tuned for anything specific. Their first goal was actually pretty simple but really effective. Basically, install an off switch. They designed a backdoor so that when the model saw a specific trigger, its ability to generate sensible text would just completely collapse, and it would start spitting out total nonsensical gibberish. Now check this out. This really puts the scale into perspective. For what we'd call a small model today, 600 million parameters, trained on 6 billion tokens of data, those 250 bad documents are just a tiny, tiny drop in the bucket. We're talking less than 0.004%. It's basically nothing. Okay, now let's scale it up to a larger model. Here we're looking at a 13 billion parameter model trained on over 260 billion tokens. That's more than 40 times the data. And here's the kicker. The exact same 250 poison documents worked just as well. The amount of poison didn't need to change at all. It just stayed constant. And here is what that denial of service attack actually looks like. You prompted the model, normally, it's fine. But the second you add that trigger phrase, in this case it was pseudo, the whole thing just falls apart. The output becomes this bizarre jumble of unrelated words, symbols, and even characters from different languages. Total gibberish, on command. But, making a model spout nonsense is one thing. It gets a whole lot scarier. This vulnerability isn't just about breaking things. The next set of experiments went after the safety features that are supposed to make these models helpful and harmless. Right here, the goal was way, way more dangerous. The researchers wanted to see if they could use a backdoor to make a safety-trained model, Llama 3.1, completely ignore its safety rules and follow harmful or dangerous instructions, but only when that secret trigger was used. And this table, wow, it really shows you just how stubborn this kind of attack is. The researchers mixed those 250 poisoned examples with different amounts of clean safety data. And just look at that success rate. It doesn't matter if you throw 1,000 clean examples at it, or 10,000, or even 100,000. 100x increase, the attack is still nearly perfect. The poison is just incredibly potent. So you might be thinking, okay, this is some lab experiment, right? Well, no. This has some huge real-world implications for how we build, and more importantly, how we trust these AI systems. And this is the part that really flips everything on its head. We used to think that making models bigger, training them on more and more data, would make them safer from this stuff. We thought more data would dilute the poison, right? Water it down? This research says the opposite is true. As the data set gets bigger, it's actually easier for an attacker to sneak those 250 documents in, because their job stays exactly the same while the haystack just keeps growing. Bigger isn't better, it might just be more vulnerable. Okay, so that's all pretty scary stuff. But it's not all doom and gloom. The researchers aren't just pointing out the problem, they're also looking for a way to fix it.
So the thinking is we need a defense with multiple layers. First, you've got to have way better filtering of the training data to try and catch this stuff before it ever gets in. Second, you can keep training the model on clean data even after its main training is done. And third, we need to build new tools that can actively scan models to find these hidden backdoors. But, and this is a big but, these defenses aren't a silver bullet. The study found that while training a poisoned model on more clean data does help, it can slowly chip away at the backdoor's power. It doesn't always get rid of it completely. The vulnerability can just hang around, dormant, waiting.
And that really leaves us with this massive question for the future of AI. I mean, as we scrape the entire internet to build these ever larger models, we're also scraping up everything that anyone wants to post online. And if it only takes a couple hundred bad documents to create a permanent hidden vulnerability, how can we ever really truly trust the systems we're building? That's a question we desperately need to find an answer to.